Everyone. It's a pleasure to be here to give you an overview of the center that I'm leading here at St. Thomas and to present some of the case studies that we've done here in Minnesota. I've already disappointed one person. The University of St. Thomas is in St. Paul, Minnesota, and we are not in the Caribbean. So sorry about that, Diane. But I'm happy to be here, and I'm looking forward to this talk. So the overview of my talk will go over a quick introduction. Then I'm going to share some device level case studies, both on the dynamics and on the transformer inrush current sourcing. Then I'll share some case studies from a system level, from a microgrid perspective, and then finally I'll quickly go over some of the expansion plans and the conclusion. So the quick background, again, University of St. Thomas in St. Paul, Minnesota. We are one of the largest private universities in the state. We have about 10,000 students, about 6,000 undergraduates, 4,000 graduates. We have an aspiration to be one of the top 10 Catholic universities in the country. And as of now, we have 1 in 6 students at the University of St. Thomas is actually in the School of Engineering, which is pretty unique for a liberal art university. We have all types of engineering on the undergraduate side, and on the master's side, we do not have a PhD program. So most of our students are either undergraduates or master's students. So the center that I lead, our mission is to be a resource to the power community to transition us to a carbon-free electricity and to produce the engineers that are going to run the grid for the 21st century. And our vision is to be one of the premier applied engineering research centers in the area of DERs and microgrids, again, looking to produce a resilient and more reliable grid for the 21st century. So our team is growing. We have now more staff coming on board. So Shri Pandey is the microgrid engineer that runs the day-to-day operations of the facility. And Omir Lordzadeh is a postdoctoral scholar. And we're growing. I'll mention later on the openings that we have here at the center in terms of jobs as well. So again, we are in St. Paul. Our neighbors are the University of Minnesota. So I see Sairaj in the audience, so he's probably somewhere there. And we are located right between downtown Minneapolis and St. Paul. In terms of our location, so St. Thomas has a St. Paul campus. That campus is cut into 2 portions. North Campus is north of Summit Avenue, and South Campus is south of Summit Avenue that you see along here. Beautiful area right next to the Mississippi. There's a bluff looking at downtown Minneapolis, so beautiful area. The microgrid is located on South Campus in the Facilities and Design Center, and it's spread out in that area. So in terms of assets, this is an aerial image of South Campus. I'm speaking to you right now from this corner in this building, FTC, along Cretan Avenue up here. That's where Xcel Energy comes in. That's the feed, 13.8 kV feed. We have a recloser along the tree line there. And this is an image of that recloser that connects us to Xcel. The microgrid right now has its own dedicated substation, and that substation is located in the Anderson parking facility right here. So we have the fuses and the disconnects along with that transformer that steps down the voltage from 13.8 kV down to 480. And this is an image of it, and that rating is 300 kVA. We also have a diesel generator in that corner of the parking facility. That's a 50 kilowatt unit. We have a load bank right between the 2 buildings right here. That's 320 kVA. It's an image of it. The solar panels are above McCarthy Gym. We have about 48 kilowatts DC solar panels, as you can see. And in the basement of FDC, we have the switchgear, which is rated for 1 megawatt. So it's a dead front switchgear, and in the back, if we open those up, you can see those 3 bus bars. Again, this is rated at 1 megawatt. For each of those breakers in the gear, we have dedicated Schweitzer 451 relays along with the Schweitzer RTACs that house the controller that we've developed in-house. The solar inverter is in the basement as well. The energy storage system is lead acid based, and its inverter is a bidirectional inverter that's rated at 125 kilowatts. So just to step back, this is a one-line diagram of the microgrid. So we have that main bus where the solar system, the ESS, and the diesel generator and the load bank connect to. And we have a couple of other buses for as test bays. We have a bus dedicated for power hardware in the loop studies, and then another bus that can go down also to 120 or 208. For the case studies that I'm gonna cover today, we're gonna concentrate mainly on the main bus here with some of those devices that we've commissioned and now we're running at this facility. And again, this is a quick simplified version. I didn't really touch upon it, but there's actually, the microgrid has its own network system through Schweitzer relays. We have its own dedicated network switches as well that allow us to monitor and operate this facility. And what's kind of unique about it is the ability for third-party testing going up to 125 kilowatts, voltage levels from 120 all the way up to 480. So in terms of some commissioning challenges, as a quick overview, a lot of the components or all of the components that I mentioned are off-the-shelf components because there's a requirement for equipment to be licensed and listed. So most of these came to us as black boxes. So from a research and development perspective, we don't really get a lot of insights into how the controller is built, what type of loops are there, all those coefficients. We're not really sure what those components contain. A lot of those equipment were either built for grid connected mode or for island mode, working alone. So the integration and the control, that was challenging, figuring out those timescales, the dynamics to make sure that things work together properly. Communication, latency, and reliability still is an issue, especially when it comes to stuff like Modbus, TCP, or RTU. Packets don't really go through the wires instantaneously, so there are latencies anywhere between 8 to 20 milliseconds sometime. And like I mentioned, power devices, which is I'm going to touch upon a bit later on. Devices have different dynamic performances, which cause transients and dynamics to be quite significant in island mode. And I'm going to cover that as well. So that's in terms of a very quick intro. In terms of device level case studies that we've done here at the center. So I'm going to first touch upon the dynamics and the timescales of each power source separately. And then since Ben mentioned 2 weeks ago, you know, a case study or the information about transformer inrush, I thought it would be a good idea to share with this group the different types of responses that we get from devices when we're talking about transformer inrush current. So in terms of dynamics and timescales of power sources, I'll go over 4. I'll cover first the utility as a source, the solar PV system, the diesel generator, and the energy storage system. The reason I'm covering utility is just to give you a kind of a benchmark on how things move in a power system. And then the other 3 are more specifically for those devices. So in terms of utility, we're looking at just loading this branch through this transformer into our load bank. So we're going to apply a load and see if that affects the frequency and the voltage that we're measuring on this main bus. So y-axis on this side, this is power, either kilowatt or kVAR. So in orange, that's my kVAR, and in blue, that's my kilowatts. And on the other side, I'm measuring the frequency in hertz. So we're stepping up the load from 0 all the way up to about 225 kilowatts and about 180 kVARs. And as we expect, the utility's frequency does not really change with loading. The ISOs out there do a good job ensuring that that frequency stays very close to 60. You can see some variation, but not that pronounced. Now, in terms of voltage, again, we're measuring here the voltage on this axis here. That's the voltage of that main bus. As we're continually loading that bus, you can see how the voltage is going down, and we're reaching up. So between no load to full load, that's about a 5% drop. And that's mainly due to that transformer, that step-down transformer between us and Excel. Now, in terms of the solar PV system, the DC source that we have here, we either have the rooftop PV system, which is at 48 kilowatts, or we have a solar emulator at 45. For the case studies that I'm going to show, we're actually using the panels on the rooftop in Makati Gym. And the inverter, that's a 3-phase 480 volt AC, rated at 125 kVA, and can do power factor between 0 and 1. And in this case, because we are connected to Excel right here, we are doing grid following. So the inverter can accept P and Q commands. So as just an example, to give you how the solar resource can vary between 1 minute sampling versus a 1 second sampling. This is a typical or an example of the output during May. So a cloudy day in May where the clouds are rolling in and out. So the panels see the sunlight and then there's overcasting on them. So if I'm sampling at 1 minute, I can see something like this. So each dot here signifies 1 minute of time. So we're seeing how we're going maybe 14 to 17, then we jump up to 23 or 24, etc. Now, if we look at the 1 second data, it's a very different story. So the variations are pretty significant. Things bounce around much more on that time scale. And in this case, we're seeing about a 15 kilowatt swing, which is about 60% of the array, because half of the array was functioning here. And that's happening in less than 60 seconds. So if your controller can't handle stuff in a sub-second, especially in island mode, you would be somewhat in trouble. Another example, kind of, especially on this side here, things look really stable and calm. But again, if you look at that 1 second data, there's a significant variation. And in this case, it's about 18 kilowatts. And that's maybe a 70% swing in less than 60 seconds. Again, just highlighting the fact that things can happen much faster, especially in island mode, and control becomes a much more pronounced issue that we need to take care of. In terms of the diesel generator, we have a Cummins 50 kilowatt unit that's also 3-phase at 480. It is being controlled by a Woodward generator. So in island mode, it can run as a grid forming entity, whether it's isochronous. So it's going to do its best to stay at 60 Hertz at all time, or using droop control. So as we load up the generator more, the frequency kind of dips more. And when we are grid connected, it runs in PQ mode. So we issue the generator a P or Q set point, and the generator follows those set points. So for the results that I'm going to show you here, we are running the diesel generator in island mode, and we are loading it up through the load bank. And we're going to look at isochronous control and droop control to see the time constants and the time scales involved. So in this case, I'm looking at isochronous control, and I want to see how fast I can move my generator when I issue set points. Is it going to be instantaneous? Is it going to be 5 seconds? Is it going to be a minute? So in red, I'm showing you the set point that I'm sending to the diesel generator, and in blue, that's the response of the generator, that frequency. Y-axis is frequency in hertz, and x-axis is time. So in isochronous control, if I go from 60 to 65 hertz, it's gonna take the generator about 45 seconds to reach that point of 65 hertz. And same thing if we drop down, if I'm at 60 and I wanna go to 55, that generator needs 45 seconds to get to that point. So it's an electromechanical device. I'm sure I'm preaching to the choir. It's slow, it needs its time to recover. Now let's look at what happens when I load the generator in isochronous control. So y-axis on this side is frequency in hertz, y-axis on the other side is load power in kilowatt. And I'm loading up the generator here, stepping up the load from 0 to about 30. And you can see the frequency dips down to about 57.2. And then very quickly recover because we are in isochronous control in less than a second. So it's pretty fast. And then when I release the load, the frequency kind of just jumps up a bit and goes back to 60, which is what we expect. So in isochronous control, that Woodward is doing its best to stay at 60 hertz at all times. Now, in terms of droop, same story, we're loading the generator, but now we've told the Woodward to run as or using droop control. So at first I apply a load of about 45 kilowatts, and you can see how the frequency kind of goes down a bit, tries to recover, but since it's in droop control, that frequency is gonna settle at 57.8 because we are almost fully loading the generator. So that's a 4%, almost a 4% droop there. To recover the frequency back at 60, we issue a frequency set point increase. And again, that generator takes its time to go back to 60. If I now release the load and have the generator at 0 load, the frequency goes up. And then I need to, again, adjust my set point to bring it down to 60. So that's in droop control. It's a good way to parallel different grid forming entities, but as you can see, frequency can bounce around a bit more if not controlled tightly. In terms of the energy storage system, the ESS, again, we have a lead acid system, which is shown here, 4 cabinets. The rating at the discharge rate of 125 kilowatt, we can extract just under 400 kilowatt hours from that bank. The inverter is a Princeton Power 125 unit. It's bidirectional, rated at 125 kVA. It can do 0 to 1 leading or lagging power factor. In island mode, it does grid forming. And in grid connected mode, it does grid following. So in island mode, I can send frequency and voltage set points. And in grid connected mode, I can send P and Q set points. And this unit actually has virtual inertia built in. And I'm going to show how we can manipulate the response time for this unit using that virtual inertia. And in this case, again, we are running in island mode, and I'm going to load up my ESS through the load bank to see the responses. So this is the frequency response of that unit in grid forming or VF mode. Y-axis is again frequency, x-axis is time. Red is my set point, blue is the actual frequency output. And as you can see, this is super fast. You can't see it on this time scale, but it's around 20 millisecond response time if I applied no virtual inertia to this unit. Here again, we're loading it up just to make sure that things are running as it's supposed to. Y-axis is active power. On this side, it's frequency. when I apply a load of 25 kilowatts, as expected, since we are in droop, the frequency should go down. And since I'm not issuing any secondary control to bump up the frequency again, that stays there. When I release the load, the frequency bounces back. Again, 20 milliseconds without any virtual inertia in this case. So now if I apply virtual inertia to this unit, and now I'm asking it to go from 60 to 62 hertz, or go from 62 back to 60, or down even to 58, when I apply my full available inertia, I can get a response. I can slow down that response by up to 30 seconds with that virtual inertia. So it kind of becomes in line with that diesel generator that we mentioned earlier. It allows the diesel generator more time to recover in terms of frequency variations. And we can see this again with loading, same thing, load testing. That frequency goes from 60 down, again, now down to a lower value, but now this unit is slower to react. And in this case, it is about 15 seconds in terms of that latency for frequency or to kind of change as time progresses. I didn't show voltages for all units, but with volt-var, or excuse me, with with the volt-var droop as well, we can do the same thing. Voltages can bounce around if we have droop, and if we are in isochronous, the voltage tries to stay at 480 at all times. So that's in terms of dynamics. Again, in terms of transformer inrush current sourcing, I'm gonna show you how we can source transformer inrush current using the 3 grid forming entities that we have here. The utility serves as our benchmark again. Then we're gonna go over the diesel generator, which is a traditional electromechanical device. And then finally the ESS, the storage system, which is an inverter. So we have 2 transformers that would need to be energized in island mode. These are T1 and T2. These are the transformers that are connected to the ESS and the solar system, and they are a delta on the inverter side, and they are Y-grounded on the main bus side. So they can help with sourcing that zero sequence current that those inverters cannot source. Both T1 and T2 are identical. They are rated at 150 kVA. 3.9% impedance, and keep this number in mind. The steady state current at 150 kVA is just under or just over 180. I'm estimating that to be at 180 amps. So we're gonna first source that inrush into T1 through the utility. So we use Excel, we power up our main bus, so now our main bus is hot, and we're gonna close CB2 to push current into that transformer. You're gonna see the voltage rise to its steady state value, and the inrush current is gonna peak at around 1,500 amps. So almost 10 times that steady state current, and it's gonna quickly decay down to about 5 amps over in about a second or 2 seconds. So since the utility has that massive inertia, it can give that transformer all the current it needs and supply that inrush without really affecting that voltage, those voltage waveforms that we're seeing on the main bus. Now, if we use the generator, again, we are in island mode. We bring in the generator, we power up our main bus, and we're gonna feed power through the main bus using the generator into T2. We close that breaker there. This is the voltage that the generator is given. You can now see some more oscillations because the generator needs some time to settle. And that inrush in this case will only peak at around 600 amps because the generator is just not able to provide that much higher current. So things don't really peak as we saw on the utility scale. And then again, that current decays really rapidly in about a second or two. Now, the big question is, can actually inverters source that massive of a current to allow the system to operate? So I'm going to show you a couple of examples of using the ESS, again, the energy storage system, that's an inverter, to feed inrush current into T1, but also into T2. So the case for T1 allows us to actually quite easily do a soft start where the inverter slowly ramps up its voltage, feeding the inrush current for that transformer to energize it. So in this case, we close this breaker and then ask this inverter to start, because the inverter has internal voltage rate limiters. You're gonna see the voltage slowly rise right here. So it's gonna take the inverter maybe 200 or 300 milliseconds to get to a steady state value. And what that results in, that current that the transformer requires, instead of it peaking at a 1,800 or 600, in this case, it only peaks at 50. So through soft starting, we can source the inrush current from the energy storage system or that inverter without really stressing out either the inverter or the transformer in this case. Much smoother, then it decays faster. Now, the question is, well, what if I use this inverter now to energize my main bus and force that inverter to give me a bigger or higher inrush current to energize T2? Can it actually do that, or is it going to trip? So in this case, again, these are closed. Those two breakers are closed, and I'm going to close this breaker to feed the current to that transformer T2. And in this case, the inverter kind of struggles. You can see how the voltage waveforms get disrupted, a lot more harmonics. But if you look down here, it's actually capable of giving around 325 amps. Even on the low side, that's close to 375. So it's able to actually energize that transformer, even though this current is almost double what the peak rated current of that ESS unit is capable of. So the inverter didn't trip. We were able to source that current into that transformer without major issues. That's for the device level. In terms of the system level case studies, so I'm gonna go over some essential microgrid functionalities. So we've done black start now many times here. We've done island mode operation. We've transitioned island to grid. We've run in parallel with Excel, and then we've done also intentional islanding from Excel. So our microgrid controller that we've completely developed in-house, we completed the alpha version, and that's in this paper down here. If you're interested about reading up about it, we are doing now the beta version, fixing some bugs, optimizing its performance a bit better. We've written that using the IEC 61131-3 language, and we implemented that in a Schweitzer 3555 RTAC. And again, it's capable of doing most of those microgrid essential functionalities. And we do operational optimization using a MILP optimization to do economic, environmental, or also volt-var. So a couple of case studies on this, on the system-wide. So let's talk about black start. Black start, everything is dead. All the breakers are open. The solar, ESS, and the diesel are off. The load bank is off. So in this case, we're gonna first start the ESS. So we start that as a grid forming asset. We're running it in Droop control. Then we close CB4 and CB5, thus energizing this main bus. So that now we have an energized bus, and the voltage at that bus is shown in this graph. X-axis is time, Y-axis on this side is active power, and on the other side is voltage. So what I'm showing you is the voltage of the main bus was 0, and then it goes up to 277, line to neutral in this case. And the ESS is just giving us maybe 300 watts, kind of just enough power to run this main bus. Step 2 is bringing in the solar. So we're gonna close CB3 and CB2, applying voltage on the terminals of the solar inverter, which is in grid following. And then we issue a command to start. When that happens, in green, you see that the solar starts up and then goes up to maybe about 7 or 8 kilowatts. And in this case, now the ESS is charging up at a rate closer to 8 or 9 or 8 kilowatts in this case. And the voltage on the main bus is still there. I'm gonna drop this moving forward because we've established that the main bus now is energized. So then we're gonna apply our loads. So we apply load in 2 increments. First, we jump up or apply a load of 35 kilowatts. In this case, the ESS starts to discharge at 25. So 25 plus about a 10 from a solar, that gives us what the load needs. We step it up again, and the ESS responds by discharging a further about 10 kilowatts too. Then finally, we start up the generator as grid forming. We're running it, in this case, in loop control. The generator starts, it produces voltage. Across CB6, we make sure that we're synchronizing the voltage between the main bus and the generator. When synchronization happens, we close that breaker, which allows us now to bring in that generator to share the power between it and the ESS. So the generator kicks in, we increase the set point once and twice to get to a point where the ESS and the diesel are almost sharing power equally in island mode. And since everything is stable and nice, no spikes, we say that black start is successful and we move the microgrid to normal island mode. And we give ourselves quick hand of applause. So again, summary, microgrid was completely dead. We were able to achieve black start in about 3 to 4 minutes, just to make sure that things are starting as they're supposed to, and we get to normal island mode. Now, if you want to go from island to grid, I'm leaving the networking out of those diagrams just to keep things simplified. But in this case, I'm highlighting 3 main connections that help us achieve this island to grid transition. So the RTAC is going to talk to the relay controlling CB1. It's also going to talk to the diesel generator and to the energy storage system. So the plot on the top, that's active power versus time. I'm showing you the 4 main power sources or sinks: ESS, solar, load, and the diesel. And on the bottom graph, I'm showing you hertz on the y-axis and time on the x-axis. To keep things not too crowded, voltage is omitted, but it's kind of the same issue as the frequency we're seeing here. Utility frequency is in red, while the microgrid frequency is in blue. You can see those are not equal. So we want to make sure that our microgrid frequency is equal and slightly higher than the utility when we want to close that breaker. So here's what's going to happen. Our frequency is far off. So first off, we need to match those frequencies. Same thing for voltage, but I'm not mentioning that here. So we're going to send the frequency set points. These are dispatched from the RTAC to the 2 grid forming entities. So first, I send a frequency set point to the diesel generator, telling that generator, I need you to produce or run at a higher frequency. So we do that. When I ask the diesel generator to run at a higher frequency, it's going to give me more power. So you see how the power rises up versus the ESS dips down. and you can see that bump in the frequency on the microgrid side. This is clear not enough. We're still way apart. So now I'm gonna issue a dispatch to the ESS to again ask the ESS to run at a higher frequency to bump up the frequency, but also to retain that power sharing. So we send that F set point from the RTAC to the ESS. That's the bump there. Power sharing kind of, the difference goes down, and you can see how that frequency on the microgrid side also bumps up. Now, unfortunately, the utility frequency now decided to go up on us. So we're gonna have to again bump up the frequency. So we sent another set point to the ESS asking it to run a bit faster. And that's gonna allow me to run faster than the utility, just a tiny bit. But that's good enough in this case. So now when the frequency and the voltage are within the bounds that we like, we issue a close command to the CB1 relay. So that close command goes there. Now that relay's job is to sit there and watch and to perform the sync check between the voltage, the frequency, and the phases on both ends of that breaker. Once the relay passively sees that synchronization happen, it's gonna close. That breaker closes, and we're gonna go from island mode. As you can see here, we went to grid connected mode because now my frequency, my microgrid frequency and utility frequency are exactly the same. And in this case, ESS goes to, and we're asking it to charge, so it's gonna set maybe at around -1 kilowatt in this case, and the diesel will run at 15. So both will switch over to grid following mode in this situation. So in terms of intentional islanding, last case study that I'm gonna go over, we are transitioning from grid connected to island mode. So that breaker is closed. We're running at about 62 kilowatts load. We're getting about 45 kilowatts from the utility in red. Diesel generator is running at 15, and the ESS or the solar is producing anywhere between 5 to 8 kilowatts on that day, and we are charging the batteries at about -7 or -8 kilowatts. So the goal to allow me to transition safely is that I want the power flow through this breaker to be 0. Realistically, we set that at less than a kilowatt. So we want that power flow to be less than 1 kilowatt for about 15 to 30 seconds to make sure that things are not fluctuating, and then we're gonna open that breaker. So the operator presses a button on the HMI for the controller. The controller runs the optimizer, and then we're gonna issue P and Q commands, both the diesel generator and the ESS system, while also accounting for the real-time values of how much power we're getting from solar and how much power we are feeding to the load bank. So those P and Q set points get issued. You can see how ESS starts now to discharge at about 25 kilowatts. Diesel ramps up from 15 to about 30, and that drives down my utility power to close to 0, and it's gonna bounce around a bit because of solar fluctuation and some fluctuation with the other sources. So when the power flow across that CB1 is less than 1 kilowatt, we're gonna send that open command from the RTAC to that relay. And we're gonna open that breaker. So you see the utility goes to 0. The diesel and ESS transition to droop control. So you see how that kind of causes a dynamic response. We are working on making this much smoother, so stay tuned for better results. But when we switch over to droop, those two devices do this dance to find the new equilibrium point. And that's a summary of that. Again, we switch over to island mode when the utility breaker opens up, and we are at a different stable point or point of operation compared to grid connected mode. So that's in terms of system level case studies. To finish up in terms of expansion plans and conclusion, it's a pretty exciting time here at the center. We got awarded a $5.4 million grant from the Renewable Development Account through the Department of Commerce. The goal for this grant is to increase the on-site power to above 1 megawatt. We're going to connect to multiple buildings on campus via a new 13.8 kV loop. We're going to expand the hardware in the loop capabilities and expand the hands-on educational opportunities as well. So we've, the Typhoon Hills, we will be purchasing 3 test beds. They should be arriving in May 2023. That's going to allow us to do some low risk and no risk R&D to further improve our protection, our control, and look at P-Hill applications as well. In terms of expansion on South Campus, this is a busy slide, but I'm showing you here actually 5 buildings. We have the STEAM complex here, or the Schoenecker Center. We have OWS and OSS here, that's the vault of that building. We have the parking ramp here, and we have the FTC building here. So we're gonna be building a new switchgear right here, close to 4 megawatts. As of now, the plan is to have 1 megawatt of diesel and around 0.5 megawatt of ESS, and building that loop 13.8 kV that allows the connection of the new switchgear to those buildings. So with this expansion that's gonna hopefully be done in about 2 years, we will be connecting to around 400,000 square feet of infrastructure here on South Campus. So we're gonna play a much more active role on South Campus, both for research and development, but also in case of an emergency, we wanna separate from Excel and keep power running on campus. An aerial image, Facilities and Design Center, Anderson Parking Facility, OWS, OSS, and then Schoenecker. That loop is gonna look something like this. That utility tunnel was finished. So we will probably start construction on that 13.8 kV loop sometime early next year or mid next year. We're gonna have an EV charging infrastructure in the parking facility. And again, going up to at least 1 megawatt, probably closer to 2 megawatts total. To show you how much this is just expanding the scope, everything that I covered through this slide fits in this little box here. All the new, especially in purple that you see is an expansion. So it's pretty exciting. It's gonna be a large project, but we are super looking forward to get this going. We're almost done with the schematic design phase. We're gonna start a design development phase in early spring. Construction documents ready by summertime, and then bidding phase and construction phase starting in 2023, and that's gonna go into late 2024. So if anybody's interested, there's a couple of job openings here for postdocs and for research engineers. Feel free to reach out if you have questions. And at the School of Engineering, we also have an opening for Professor of Practice. It's a limited term position. So also feel free to apply there. That's specifically for power systems. And with that, feel free to reach out if you have questions. And you can also follow the center on LinkedIn. And that's all I had for today.
Thank you so much, Mahmoud. That was really great.